Hi, this is Barb Aichinger from FuturePlus Systems, and welcome to MemCon 2014. Today I'm going to talk about performance measurements for DDR4 based systems. DDR4 memory is pervasive in cloud computing, and measuring performance has become more critical. We can now log events on every cycle, so in reality we have created more of an analytic versus just a measurement. Some in the industry say that DDR4 is the end of the DDR line. If so, we just can't keep going faster. We need to work smarter, not harder. So now the problem shifts. How can we improve performance without going faster? Well, let's take a look at the traditional performance measurements. They are power management, latency, and bandwidth. What I'm going to propose today is some new metrics. So we want to work smarter, and in order to do that, we need to measure what we have today. We need to look at our traditional metrics like power management, latency, and bandwidth, but we also need to consider new metrics like page hit analysis, multiple open bank analysis, bank group analysis, bank utilization, and what events the system performs during a boot, since it can take a considerable amount of time to reboot servers once they go down. To better explain these metrics, let's measure them on a real system. The target I used was a brand new Asus X99 DDR4 based system. It has 4 memory channels, but for this experiment I used only one. In that channel I had a single DIMM, 2 rank, 8 GB. In order to create a lot of memory traffic, I ran the Google Stress app. To make the measurement, I used the FS2800 DDR Detective from FuturePlus Systems. The DDR Detective is the only tool on the market that can make these measurements, and that's because it uses counters instead of the traditional approach of using trace memory. Trace memory is quickly exceeded in today's fast systems. To capture 1 second would require 4.5 gigabytes of trace depth. 1 hour would require 270 gigabytes. This is expensive and slow. By using large counters and counting events and the time between events, we can achieve hours and days worth of metrics with no trace buffer memory and no time-consuming post-processing. Let's take a look at power management. While running a memory test, we are not going to see a lot of power management, given that this DIMM is very busy. Over a second, we can see very little idle time, mostly active, and in this system, DLL has been disabled. Here's what power management looks like when the system is idle, an important metric for servers since lowering energy costs is key. Now we can see pre-charge power down, active power down, and the fact that the ranks are symmetrical. What we don't see is also telltale. We do not see the memory going into self-refresh or max power savings. DDR4 has an enhanced power savings protocol. You will want to make sure your system is using these modes. A conservative estimate is that there are approximately 50 million servers worldwide. With each server having 16 to 24 DIMMs, that equates into 800 million to 1.2 billion DIMMs in today's data centers. Even a small power savings can add up. Just ask Facebook. When their engineers save only a single watt per server, it adds millions of dollars to the company's bottom line, and shareholders certainly like that. For high performance, you want to minimize latency on consecutive transactions. However, if commands to the DRAM are too close together, the DRAM will not have time to react and data corruption will occur. The JEDEC DDR4 specification defines these minimums. For high performance, you want to operate at these minimums. Let's measure our system's latency. The DDR Detective is multi-purpose, and we can use the compliance violation feature to make these measurements. We simply shmoo the minimum values, and when the system operates at these values, the counter will increment, allowing us to determine the latency. Here are the results. You can see that for read to precharge and write to precharge, the system operates at the minimum. However, the other metrics are close, but could be closer. Saving 1 clock out of 100 is a 1% 5% performance improvement. And for today's critical applications like banking, military, and safety, this performance improvement could be critical. When deciding what latency parameters to focus on, we need to take a more detailed look. In the previous slides, I showed how the DDR Detective can schmoo the latency values to determine where the system is operating at. It can also trigger on those values and show exactly, down to the command and signal level, what is happening for this event. We can see that although the system was operating above the minimum by 60% for consecutive writes to different ranks, it was using that time to precharge or close banks. By closing unused banks, the system is saving power. So when evaluating performance, be sure to consider your power management goals. Well, we had so much fun measuring those latency parameters. Let's look at a few more. We used the same technique and quickly determined where this system excelled and where improvement might be made. So I can summarize latency by saying that good designs that use quality parts don't need margin. They can safely operate on the edge of the spec. But as you saw, trade-offs with power management will naturally occur. When we examine the bandwidth of a memory channel, we need to define and identify overhead. Since the main purpose of the memory is to read and write data, everything else is considered overhead. This would include the command bus. Now, the command bus and the data bus can operate simultaneously. Data bus utilization would be the percent of time actual read and write data is being transferred. Bandwidth is the amount of data transferred per second. Here's what is happening on the command bus while running the Google Stress App memory test. You can see that this software is accessing all of the banks within the ranks pretty equally. The DDR Detective counts every access and tells us what it is. We can see that the system is only doing 8-beat data bursts versus a burst chop, which is only 4. We can also see that the reads are approximately 2x what the writes are for this past second. For this view, I have removed the deselects so you can see more clearly the read and write traffic. Once I add the deselects back into the chart, you can see that they dominate the picture. The majority of the time, the command bus is idle. By exporting my data from the DDR Detective into Excel, I can quickly see the big picture. The command bus, by design, is largely unused. So if I were working on future memory architectures, I might take a look at how the command bus might be used to increase performance. Let's look at the data bus. This is the whole reason for memory to exist, to store and transfer read and write data. Since the command bus dictates what is seen on the data bus, the distribution of commands will look similar. We can see that the reads are approximately 2x the writes, and the data is evenly distributed across all banks and ranks. This view is useful to see if your system is write optimized, if that's what you are aiming for. Also, in a chip kill or page retirement scenario, you could quickly see how the traffic is reallocated. Here's our summary. You can see that 12% of the memory channel bandwidth is unused. This is excellent, as a certain amount of spacing between commands is necessary, as we saw in our latency measurements. We can see the breakdown of reads and writes per rank is nearly equal, as we would expect from a memory test. The output of the DDR Detective is very detailed, and if we needed to, we could see the breakdown of the traffic on a bank basis. So now finally the slide you've all been waiting for. What is the bandwidth of a single channel, single DIMM in a new DDR4 based system? It is a whopping 13.5 gigabytes per second. So as I mentioned, power management, latency, and bandwidth are the 3 traditional performance metrics. But because we now have tools that allow us to measure every clock cycle on the memory bus, we can dive deeper and gain more insight into how to make our hardware and software better. The next three metrics I'd like to discuss are page hit analysis, multiple open bank analysis, and bank group analysis. Here is page hit analysis. A hit is identified as an access where the page was already open, whereas a miss is where the memory controller had to issue an activate command, which opens the page prior to access. Unused is where the page was opened then closed, but never accessed. Memory controllers use various algorithms to increase hit rates by opening pages that they think will be needed. In this case of unused, it's clear they guessed wrong. Page hit analysis is a powerful measurement and can be used to evaluate memory controller hit-miss algorithms against workloads so that hardware and software can be tuned for higher performance. Here is a summary of 1 second's worth of runtime. From previous slides, we know that the read traffic was approximately 2x the write traffic, so we would expect the hit rate for writes to be half. Since it is greater than half for hits and less than half for misses, it tells us that under these circumstances, the system performs better for writes from a hit-miss perspective. Also, by studying the unused and making changes, the system could see an immediate performance improvement. Next up, multiple open bank analysis. This is another never-been-done-before measurement. It tells us how many banks are open simultaneously and for how many cycles. Open banks are great for performance because it improves the hit rate. Not so great for power management, as open banks burn more power. This metric can be used to evaluate how good the system is at allocating memory resources and can be used to compare different systems under the same or different workloads. For DDR4, the number of banks was doubled from 8 to 16, and the concept of bank groups was created. Each bank group contains 4 banks. Latency on consecutive accesses to the same bank group is longer than consecutive accesses to different bank groups. So going to different bank groups on back-to-back accesses is the performance path. So for DDR4, bank group access analysis is key for performance. The system performed well for this metric as the vast majority of consecutive accesses were to different bank groups. Bank group tuning can be accomplished from both a hardware and software perspective by using this metric. But wait, there's more performance metrics that we can measure. Bank utilization. This gives a summary of traffic allocation, especially important when looking at system reliability. What happens when chip kill or page retirement occurs? How does the traffic reallocate, and what are the performance implications? This gives us an overview from a bank perspective. Bank utilization can also identify system hotspots and can potentially identify a row hammer situation, which is excessive activates to a single row address. That can cause undetected data corruption if done within a retention cycle. Lastly, we have bus mode analysis, which can help us create a faster boot time. Here's our bank utilization while running the Google Stress app. As you would expect, we see a high rate of open banks, and all are being accessed about evenly. This is in contrast to an idle bus, which shows uneven and much lower accesses. Lastly, we have bus mode analysis. This can show us second by second where the system spends its time while booting. For example, how long it spends training the memory and in write leveling. Rebooting systems in a data center is a time-consuming task. By understanding where the system spends its time, we can learn where we need to make improvements. You can also answer the question of why one system boots faster than another, and perhaps figure out why a system didn't boot. During this presentation, I've given a lot of information with the goal of advancing the state of the art. We are now on our 4th generation of DDR memory. Memory controller and system architecture has evolved. Can this information lead to better designs? Could we create a dynamic memory controller architecture based on workload? Also, which software to run that stresses the system and best shows architectural flaws? I chose to run the Google Stress app, but I'm sure there are others. So to summarize, we've added some new performance metrics to add to the traditional metrics of power management, bandwidth, and latency. These new metrics are made possible by new tools like the DDR Detective that uses counters instead of trace memory and never misses a clock cycle. To learn more about the DDR Detective, check out the DDR Detective website and the FuturePlus.com website. And thanks for listening to my MemCon 2014 presentation on DDR4 Performance Metrics.